Hello and welcome back to Unit 11. In this part of Unit 11, we're going to look at constant angular acceleration. To begin with, we're going to write down the equations for constant angular acceleration, which are going to look very familiar. The first equation allows us to relate the angular position to the initial angular velocity and the acceleration. The next one relates the angular velocity at a time t to the initial angular velocity and the acceleration. And the last one allows us to remove time and find the angular velocity at a time t based on the positions and the velocities. And look, I had x's sneak in instead of thetas. Okay. These equations are identical to the previous version of constant acceleration equations we have, with the linear variables changed out for the angular variables. So everything you learned to do in the past with these equations apply here as well. We're now going to work two examples using these equations. The first is for a table saw. So a table saw typically runs at about 3,500 RPM. If we assume that the table saw starts from rest and accelerates uniformly up to this speed in about a second and a half, what is the angular acceleration of the blade and how many revolutions does it complete in that time? We can draw a picture. So here I have my table saw blade. I know, doesn't have many teeth, not going to cut very well. Okay. Let's assume that it rotates this way. That will give us an angular velocity per the right-hand rule, or an angular position and angular velocity per the right-hand rule pointing out of the page. And given that this is increasing angular speed, alpha should be in that direction as well. So we're going to define that direction as positive. Okay. I can now write my grocery list. Just as we had when working with these equations linearly, we are free to put our 0 for position anywhere we want. So I'm going to put it at 0, or I'm going to make the initial angle 0. The initial angular velocity, we're told, is from rest. So this is 0 radians per second. Omega is going to be 3,500 RPM. So 3,500 revolutions per minute times 1 minute is 60 seconds times 1 revolution is 2 pi radians. And that works out to be 366.52 radians per second. The last piece of information I'm given in this problem is that it takes a second and a half, 1.5 seconds for time. And I want to find the angle and the acceleration. Let's begin by finding the acceleration. The easiest way to do that is to use the omega equals omega naught plus alpha t formula. So 366.52 radians per second equals 0 radians per second plus alpha times 1.5 seconds. And that gives us an angular acceleration of 244.35 radians per second squared. To find the angular position, the easiest way to do that is to use this equation. Now that I know the angular acceleration. Initial angle we set to be 0. Initial angular velocity was also 0 because it started from rest. Alpha was 244.35 radians per second squared. I need to multiply that by 1.5 seconds squared. This tells me that I move through an angle of 274.89 radians. But the question asked how many revolutions. So I need to do a unit conversion that 2 pi radians is 1 revolution. And that works out to be 43.75 revolutions. For the second example, we're going to look at a CD player. Typical CD player rotates a CD at about 500 RPM. We want to know how far does a point on the edge rotate if the CD player takes half a second to come to a stop. And we're told the radius of a CD is 4.5 centimeters. So again, here's my CD. I'll even put the hole in the center. Angular position and angular velocity are going to be in one direction, but because it's slowing down, angular acceleration will be in the other direction. So I need to expect my alpha to have a negative value compared to my initial velocity. I'm going to let the direction of the initial velocity to be positive. And now I can write my grocery list. I think I will write it over here instead. More room. Okay. Again, I'm now allowed to put my 0 through anywhere I want in the rotation. So I'm going to start at 0. 500 RPM is equivalent to 52.36 radians per second, following the same unit conversion I used for the table saw problem. That, in this case, is my initial angular velocity. My final angular velocity is 0 because it comes to a stop. And we're told it takes a half second to complete this process. I want to find how far does it rotate. So that is a measure of arc length. How far around does it go? How much distance does it travel? In order to find arc length, I need to find angle. But I don't have the angular acceleration. Therefore, my first step is going to be to find that. Final angular velocity is 0. Initial angular velocity is 52.36 radians per second, plus alpha times half a second. Solving gives that the angular acceleration is negative 104.72 radians per second squared. And it is negative as expected because it should point in the opposite direction of the initial velocity, given that this is slowing down. Now I can proceed with finding the angle through which the CD rotates using this equation. Our initial angle we set to 0. The initial angular velocity was 52.36 radians per second multiplied by half a second, plus 1/2 of negative 104.72 radians per second squared times half a second squared. Multiplying and adding as appropriate, this works out to be a change in angular position of 13.09 radians. And again, converting radians to revolutions, because that is what is requested in the problem, gives me that that the CD completes 2.08 revolutions. If we are looking at a point on the edge, we can find how far it travels in that by multiplying the change in angular position by the radius. When working with this, even though we know that it is 2.0 revolutions, we need to use the angular position in radians. So that was 4.5 centimeters times 13.09 radians. 4.5 times 13.09 is 58.91 centimeters. So a point on the edge of the CD will move 58.91 centimeters as the CD slows down.